So this is starting chapter 2, the lecture for this. So here is some review material that you're going to need to be familiar with. So there's not a big emphasis on the history of the atom on the AP tests. I'm going to kind of eliminate some things in chapter 2 that you don't really need to know. But to kind of quick review, back in the 1800s, we have Dalton's atomic theory, and he was kind of one of the first ones to kind of put things down as to how the atom is structured. So these 4 parts of the atomic theory, each element is made up of tiny indivisible particles called atoms. So at the time, they thought the atom was the smallest thing. We now know atoms contain protons, neutrons, and electrons, and they go smaller than that, stuff that we are just not going to talk about in this class. But again, Dalton had a first idea of that they were indivisible, the atoms were. Number 2, atom of a given element are identical, and I guess you're probably thinking, well, that's kind of redundant, but at the time, nobody had really said that or stated that. So again, atoms of different elements are different in some fundamental way or ways. Again, at the time, that was kind of revolutionary. Number 3, chemical compounds are formed when atoms of different elements combine with each other. A given compound always has the same relative numbers. So again, even back then, they kind of understood kind of a compound had a certain number of each one of the atoms in there. Again, they just may have not had as much extensive testing in terms of their theory. And finally, number 4, chemical reactions involve reorganization of atoms, changes in the way they're bound together. Atoms themselves are not changed in a chemical reaction. Do we know that to be true today? Is there any place where an element actually changes itself, the atom itself? Again, you might say nuclear chemistry, and on the AP test, they've taken nuclear out. It is in your book. I wish it was in here, but it is now pushed into AP physics land for nuclear discussion of alpha, beta, gamma, and other things. But we can change fundamentally the atom. We could create new matter. We do have that ability now. So law of conservation of mass, of course, Lavoisier, French. You will find that I cannot do French. Scientists who kind of did some experiments and figured out that the mass that they thought they were losing when they were doing experiments was actually just a gas coming off, or they couldn't really measure things. But the total mass actually remained the same constant during a chemical change. Now, these next 2 are a little bit more involved, so I'm going to spend a little bit more time on this one. Law of definite proportion. Proust figured out that a pure compound always contains a definite or constant proportion of the elements by mass, okay? And please remember that this is by mass, so we're doing grams here. We haven't talked about the mole yet. So if I have a compound that contains fluorine and sulfur, okay, so compound 1 has 2.66 grams of fluorine and 1 gram of sulfur, a total mass of 3.66. Compound 2 is 3.96 fluorine and 2.98 grams of sulfur with the total volume of 6.94 grams. So what law of definite proportion says, if I'm looking at their masses, can I say that they are the same compound based off of their masses? So if I wanted to take 2.66 and divide it by 3.66, I will get around 72.6% is fluorine in that first compound. So if compound 2 was supposedly the same compound, it should have the same amount of fluorine. But if I take 3.96 and divide it by 6.94, you're probably already guessing, it does not come out to be 72, it's around 57. So because of that, these have to be different compounds that we are looking at. So that is true of every compound that we know, that it has a definite proportion in terms of the elements. So the next one is law of multiple proportions. This one I think is a little more tricky to kind of explain compared to definite proportions. So again, it kind of goes back to what Dalton was saying in his atomic theory. When 2 elements A and B form 2 different compounds, the amount of A that is combined with a fixed amount of B is in a small whole number ratio. Okay, So again, I'm going to use compound 1 and 2, but I kind of changed the numbers here, so please understand that it looks different than the previous problem. Compound 1, I have 2.66 grams of fluorine to 1 gram of sulfur. I have 1.33 grams of fluorine to 1 gram of sulfur. Now, I purposely put these to 1 grams of sulfur so we could actually just look at the fluorine and compare those. So what you're talking about is if fluorine and sulfur can make two different compounds, those compounds, that ratio has to be a whole number. So if I look at compound 1, okay, versus compound 2, and I look at their amount of fluorine, 2.66 grams of fluorine to 1.33 grams of fluorine in compound 2, this has to come out to be a whole number. So this comes out to be a 2-to-1 relationship. So I have twice the amount of fluorine in compound 1 as I do compound 2. So anytime you're comparing the same element in two different compounds, they will come out to be whole number ratios. Now they're not going to be just 2-to-1, they could be 3-to-2, but it's always going to be a whole number ratio, okay, whole number ratio. So some examples of this are things like carbon monoxide versus carbon dioxide, okay? So you have twice the amount of oxygen as you do here. Water compared to hydrogen peroxide, H2O2. That has twice the amount of oxygen as it does here. One that we will do a lab on, okay, is copper 1 chloride versus copper 2 chloride. So you should have found that you have twice the amount of chlorine in one of the compounds versus the other. So it's always going to be a whole number ratio when you're looking at that, okay? And again, we're looking at grams here. So more review material. Now we get into the 1900s. We now know that they're made up of atoms, but we now have subatomic particles that we're going to talk about. So diameter of an atom, 1 to 3 angstroms. So again, this is a unit I showed you in lecture 1. It's between 1 and 3, 10 to the negative 8th centimeters in terms of diameter. Again, you don't need to know those numbers, but I want to throw out some things at you so that when you see them, when we get into trends, it's not unfamiliar to you. Protons have a positive charge, of course. Their mass and their charge is written here. Again, I don't want you to focus on the actual numbers. That's not going to be what we look at. Instead, I want you to focus on what is essentially the relationship between these three. So if you look at the protons and the neutrons, they have the same mass. Okay, and those are both found in the nucleus, so they have the same mass, but the mass of the electron is vastly different. It's 10 to the negative 28th, and these are 10 to the negative 24th. Other thing I want you to recognize is protons are positive, electrons are negative. They have the same amount of charge, so it's called a coulomb. We will talk about that later on. But again, these numbers are not going to be something you need to memorize or know. I'm just showing you the numbers to show you what the relationships happen to be. Also review, atoms of different elements have different number of protons. So again, when we're looking at a periodic table, your atomic number is usually listed on the top, depending upon the periodic table that you are looking at. Mostly that's where they put the atomic number. Do note that we also have things called isotopes, and these are atoms with the same atomic number, but they have different number of neutrons. So that's going to be, again, something that we talk about. So there is different ways of writing isotopes. So if I have chlorine, it has two different isotopes, chlorine 35 and chlorine 37. So what you will see typically for the isotopes is you will see what we call isotope notation. Mostly you will see it in this format, but you could also see the word written out or the element written out and a dash and then a number. This number is called the mass number, and that is the number of protons and neutrons in that particular isotope, okay? So this is your mass number on top, and on the bottom, if you see it sometimes, it is your atomic number. So that's the number of protons. So if that's the number of protons and that's the number of protons and neutrons, when you subtract those two numbers, you end up with the number of neutrons. Okay, so isotopes, again, are not found on the periodic table. You have to actually have another resource for that. So please note that they have different number of neutrons. And to finish up this part here, we have ions. We have things that have different charges. So remember, cations are positive, anions are negative. The way I always remember cations as being positive is the T looks like a plus sign. If you had another teacher, usually they do cations are positive, as in the paw itself is positive. I don't care how you remember it. But cation and anion are losing or gaining electrons. They are not changing the number of protons. But do remember that the atomic character of the element itself is due to its protons, so that tells you exactly what element it happens to be. But do always know that the chemical properties that we are going to be exploring in this class have to do with our friend the electron. That is the most important part. That is what we as chemists look at, is it's all about the electron, all about the electron.